Welcome all. This is the third lecture on fluid mechanics. This is our question series for GATE 2023. So straight away, let's go and start discussing some good questions. Okay, let's take the first question. Read the question. Consider an incompressible flow of a constant property fluid over a smooth, thin and wide flat plate. The free stream velocity. First question is very simple question. So slowly we'll move to some tougher questions. The free stream flows parallel to the surface of the plate along its length and its velocity is constant. Okay, free stream velocity is constant. Okay. The value of Reynolds number at a distance of 2 meter from the leading edge of the plate is 8000. Okay. The flow within the boundary layer at a distance of 1 meter. There is no need to put pen on paper. It is a simple question. There is a plate and the fluid is flowing parallel to the plate. This is the free stream velocity. Okay. Now, he said all distances are measured from the leading edge. Okay. Now, at a distance of 2 meter, let us say this is 2 meter. This is our 2 meter. At a distance of 2 meter, let this be the boundary layer. I don't know how far it is laminar, how far it is turbulent. Okay, chalo. Now, at this section, which is 2 meter from the leading edge, the Reynolds number is, at this section, the Reynolds number is 8000. This is an external flow. Observe carefully. Flat plate. The fluid is flowing over a flat plate. This is an external flow. For external flows over a flat plate, we know that for laminar boundary layer, the Reynolds number must be less than 5 into 10 power 5. What does it mean? And the Reynolds number is also given by rho u infinity x by mu. Clearly, he used one term, constant fluid properties. Means density is not changing, mu is not changing. And he also said constant free stream velocity. Observe here. So, please observe here, the free stream velocity is constant, so u infinity is also constant. So it means my Reynolds number is purely a function of x. So as x is increasing, the Reynolds number is increasing. So for laminar flow, the maximum value of x that can occur. So if you want pure laminar, it should be, that will be the maximum value of x. If you want the Reynolds, Reynolds number 5 into 10 power 5, that x will be maximum. Less than that x, it will be laminar. So look at carefully. The length is 2 meter and at this length, the Reynolds number is 8000. So you tell me when x is, so at a distance of 2 meter, the Reynolds number is 8000. What will be the Reynolds number at a distance less than 2000? It's all laminar. It's all laminar. So very easy asking. So within the boundary layer, the flow within the boundary layer at a distance of 1 meter. Means at 2 meter, it is 8000. Means at this it is less than 5 into 10 power 5, so it is laminar. So if it is laminar here, yes, there will be laminar further up to 5 into 10 power 5, but he is asking at 1 meter. So already this is completely laminar boundary layer. So the Reynolds number is 8000. So there, please, some students, they get confused. Sir, if it is more than 4000, it is turbulent now. That is for internal flows, that too through pipes. So this question was asked by so many students. They get confused with external flows and internal flows. Purposefully, I have taken this question because some students suddenly, why this question is taken, there is a reason for this. Suddenly they think that more than 4000, it is more than 4000, it is turbulent, but that is through pipes, for flow through pipes. So as it is laminar up to at 2 meter, so within that 2 meter is also laminar. So he's asking at 1 meter, so it will be laminar. It is a simple straightforward question. Chalo, let's go to the next question. Let's go to the next question. Please read this question. This is a good question. This is a good question. Consider a steady laminar fully developed. Observe this, fully developed flow of incompressible Newtonian fluid through a horizontal straight pipes 1 and 2. There are 2 pipes 1 and 2 of circular cross section. The volume, this term is very important. The volumetric flow rates in both pipes are equal, same. What is same? In both pipes, the discharge is same. I repeat, in both pipes, the discharge is same. Okay. if the diameter of the pipe 2 is twice that of 1, so second pipe diameter is 2 times that of the first pipe diameter, the ratio of shear stress at the wall of pipe 1 to the shear stress at the wall for second pipe. What is he asking? Let me do this. He is asking the diameter of the second pipe is given as twice the diameter of first pipe. So can I write the radius of the second pipe is twice the radius of first pipe? Yes, because diameter is twice the radius. I repeat, my dear students, diameter is twice the d. I'll write it as twice the radius is equal to 2 times. What is the diameter of first? 2 times the diameter of first. So therefore, the radius of second pipe is twice the radius of first pipe. Wonderful. One thing is constant, he said, and moreover, please see the flow is laminar. The flow is laminar. Okay, no problem at all. No problem at all. So this is the relationship between the radii of both pipes, and the flow is laminar, and moreover, the flow is fully developed flow. Fully developed flow. Okay, chalo. Now, clearly he said discharge or volumetric flow through both pipes is same. Okay, no problem at all. When I discussed in our regular plus classes, I had derived every equation for discharge in laminar flow, and that is given by pi u max r square by 2. I gave this equation. I don't know whether you remember or not. So this was the equation, or if you do not remember, I will explain in a different way. Discharge can be written as, dear students, area into velocity. Area is pi r square into average velocity. This is for the first pipe, and that is equal to, what is discharge area? Pi r square into velocity, average velocity. Whenever I multiply the complete area with velocity, it will be average velocity. So this is my equation. Okay, and you also know for laminar flow, the average velocity is half of the maximum. So therefore, pi r square and the average velocity is half of the maximum. This is for the first pipe, and that is equal to pi r square. What is the average velocity? Maximum by 2. And this is for the second pipe. No problem at all. I think pi by 2 can be cancelled. This is r for the first pipe, u max for the first pipe. So I'll write radius of the first pipe, maximum velocity in the first pipe is equal to this is r square. R square u max for the first is equal to r square u max for the second. Wonderful, sirs. No problem at all. Wait. I have already given you the equation for maximum velocity. It is 1 by 4 mu minus dou p by dou x into capital R square. This is the radius of the pipe. I gave this already. I have derived this equation. Now it is a question series, therefore I am not deriving the equation. This equation was derived by me. Okay, let us put it here. So therefore, R1 square, okay, u maximum, 1 by 4 mu minus dou p by dou x r square. This is for the first pipe, should be equal to r square. This is second pipe radius into u max for second. What is this? Is the general equation for u max. So therefore it will be 1 by 4 mu minus dou p by dou x into r square, and this is for the second pipe. Wonderful, sirs. Now wait. Please do not cancel this dou p by dou x and this dou p by dou x, because pipes are different, but it is a fully developed flow. So therefore this value for a given pipe will be constant. Now same fluid is flowing, 1 by 4 mu can be cancelled. So I will write this as R1. Wait, R1 square. So R1 power 4 square into minus dou p by dou x for first pipe is equal to R2 square. This is R2 square power 4 square into minus dou p by dou x for second pipe. Wait. Now what do you want? Please look at. Please observe what is the ratio of wall shear stress for pipe 1 to pipe 2. Look at the shear stress at the wall, which I write it as tau naught, or this can also be written as, dear students, This can also be written as tau w, doesn't matter, tau wall is equal to minus dou p by dou x into R by 2. This was the equation that I derived in laminar flow. So the wall shear stress for laminar flow is given by minus dou p by dou x into R by 2. Wait. Now, I got this condition. Now what is he asking? Wall shear for 1 to wall shear for second pipe he is asking. So what do I write? It will be minus dou p by dou x of 1 into R1 by 2 by, just substitute wall shear as this, minus dou p by dou x of second pipe into R second by 2. Wonderful. Wait. Now this two can be cancelled. I want this value. He is asking this value. एक बार observe करना. Minus minus can be cancelled. Okay, कोई बात नहीं. इधर देखो. From this equation, what can I get? Minus dou p by dou x R1 minus dou p by dou x R1. So I will write this as the same equation. I will write this as R1 cube into minus dou p by dou x of 1 into R1. Look at, please observe, R1 cube into R1 is R1 power 4 is equal to R2 cube into minus dou p by dou x of second into R2. Observe, R2 cube, R2 power 4. अब क्या चाहिए? Minus dou p by dou x R1 by minus dou p by dou x R2. This will be, so if I want this value, if you want this value dear students, अगर ये value minus dou p by dou x R1 minus dou p by dou x R1 by this value, I want this divided by this. So what do I get? This by this will be R2 cube by R1 cube. So this will be R2 cube by R1 cube. But already the second pipe diameter is twice of the first. So R2 can be written as 2R1. But I have cube here. So cube by R1 cube. So therefore, this R1 cube, this R1 cube gets cancelled. Now you are left with 2 cube, which is nothing but 8. This is a good question, sirs. So the answer is 8. Is it clear, my dear students? Wonderful question. So wonderful question. Let's proceed. Let's proceed. Now, next question. This is a good question, sirs. This is a good question. I thought of sharing with you this question. Please read the question and first try to understand the question. A student performs a flow experiment with Bingham plastic fluid under fully developed laminar flow. Whenever the flow is fully developed, the pressure gradient dou p by dou x will be constant. Okay. In a tube of, it's not R, in a tube of 0.01 meter radius with a pressure drop of 10 kilopascal over a length of 1 meter. So what is given? The pressure drop per unit length. Look at, what is the pressure drop? It is 10. Kilo means I'll write it as 10 power 3. I repeat, 10 kilopascal. Kilopascal can be written as 10 power 3 pascal, 10 power 3 pascal by length is 1 meter. This is the one. So what is the unit of this? This is Newton per meter square and this is meter. So Newton per meter square, that is Pascal. So this can be written as Pascal per meter. That is given. Actually it is a drop which is actually minus. Actually it is a drop. So therefore I'll write it as minus because it is a drop. No problem at all. So directly it is given minus dou p. Minus indicates drop. Okay. Now over length of, if the velocity profile is flat for R less than RC. Wait, sirs. This is the center of the pipe. And the radius is measured from the center. What is he saying? The velocity profile is flat for R less than RC. Look at carefully. This profile is flat. Up to what radius it is flat? R less than RC. This is the center and this is RC. And up to RC, the profile is flat. After RC, and for R greater than RC, the profile is parabolic. See, my dear students, let me change the color so that you can visualize easily. हाँ, ये color ले लेंगे. अब देखो, This is parabolic. This is parabolic. So the profile is something like this. Profile is something like this. It is linear here and it is parabolic. It is parabolic. Can you see? Yes, it is parabolic. Okay, I'll change the color also. So let me check with this color. So it is parabolic, then flat, then parabolic. Understand carefully. Up to the radius of RC, from 0 to RC, I repeat, from radius 0, that is center, to RC, this radius is RC, it is flat. It is flat, means there are no velocity gradients in this region. In this region, इस region में there are no velocity gradients, but once it crosses RC, it is parabolic. Okay, no problem at all. And consider R and X as the radial. R is radial and X is axial direction. And the shear stress is finite as R approaches 0. My dear students, for a Newtonian fluid we have seen along the central axis the shear stress is 0. But this is Bingham plastic fluid. What is he saying? See, please read, try to understand the question rather than giving answer. So the shear stress is finite as R approaches 0. So at the center, definitely there is a shear stress. Now, what is he saying? And he has also given a force balance. When you take a free body diagram and analyze forces, the force balance has resulted an equation of something like this. So let me take this equation and go to the next slide. What is that equation? Look at that equation says d of r tau by dr, d of, I'll change the color, d of r tau by dr, okay, d of r tau by dr is equal to r into minus dou p by dou l is equal to r into minus delta p by l. Let me check whether I wrote correctly or not. Minus, okay, where tau rxy is the shear stress, and look at क्या बोलता है, and if rc is 0.001, he is talking about this value is 0.001. What is the magnitude of yield shear for this Bingham plastic? So let me explain. This is a very good question. Let me explain. See, actually what is happening, this is the pipe. Let me explain the problem. Try to understand the problem. Okay. Now this is the central line. Now, he said up to some radius, the velocity profile is flat. Then it is parabolic, something like this. And this radius is RC. And from here we are measuring R. Okay, no problem at all. If you observe the profile carefully, let me show you the Bingham plastic wala. Here we have velocity gradient and here you have shear stress. And the Bingham plastic fluid is something like this, and this you call it as yield shear, tau naught. What does it mean? So physically, what is the meaning of this graph? It means up to this shear stress, there are no velocity gradients. Our du by dy values are 0. Means there is a shear stress. Look at carefully, sirs. Bingham plastic is not a classical fluid, because the definition of a classical fluid is even if there is a smallest shear stress, it should flow. But understand carefully, there are no velocity gradients in this. So this shear stress you call it as yield shear stress. And once you cross this tau naught, once this tau naught is crossed, now there are velocity gradients. And observe here. Dear students, from radius r to rc, what are the velocity gradients? It is absolutely flat. The velocity profile is flat, means here, everywhere the velocity is same, means there are no velocity gradients. It is something like this. Once I cross RC, up to RC, there are no velocity gradients. You observe the profile carefully, sirs. If you observe the profile carefully, this is the profile. So up to, this is the radius, from center I am measuring, this is the center. So up to this radius, if you see, up to this RC, Everywhere the velocity is same. But afterwards, now the velocity is, look at, now the velocity gradients are coming. It means indirectly he is asking us to calculate what is the shear stress at R is equal to RC, because when you cross that, there are velocity gradients. So therefore, this is our yield shear stress. When you cross, you are getting velocity gradients. When you cross, you are getting velocity gradients. When you cross this, you are getting velocity gradients. Here the velocity is different, here the velocity is different, here the velocity is different. Look at, there is a change, but here it is flat. So please observe clearly. So indirectly in this question, he is asking, what is the shear stress when R is RC? That's it. Because once you are crossing this, please observe the profile. एक बार profile को देखना. Profile is something like this. You tell me at this radius, what is the velocity? Same. You see this vertical line? Same. So this axis is radius and this axis is velocity. And once I cross this, here the velocity is different. Look at the x distance is varying. Here the velocity is different. Here the velocity is different. Means you are getting gradients. Gradient means change in velocity with radius. So you are getting change of velocity only when you cross RC. So only when you cross this. So this is my yield shear stress. Means he is asking what is the shear stress? Yield का मतलब यहाँ का shear. Let me do that. Hope you have understood. Up to this, there are no velocity gradients. When R is RC, up to RC, no velocity gradients. If you see the graph, up to this, there is no velocity gradient. Once you cross RC, velocity is changing. Once you cross, velocity is changing. Means this shear stress is your yield shear stress. So let me try to calculate the yield shear stress, my dear students. And rest is just, analysis is very important. Rest is simple calculation. Let me calculate. Now let us try to integrate this equation. एक बात देखो, इसको integrate करेंगे. So what I do? D of R tau is equal to R dr. I am bringing dr to this side minus dp by L. You know it is a fully developed flow. So this term will remain constant. The pressure gradient term will remain constant. Please integrate this equation. If I integrate, there is a differentiation. So therefore, if I integrate, this differentiation will go R tau is equal to, what is R dr? This is constant because fully developed, this is constant. R dr is R square by 2 minus del P by L plus C. Wonderful, sirs. Wonderful. Now let us take the radius 0. Let us try to find out the boundary condition. R is measured from the center of the pipe, center. So when R is 0, एक बार देखना. When R is 0, shear stress is not 0, sirs, because it is a Bingham plastic fluid. When R is 0, this is not 0. This is finite. So there is a finite shear stress here. So it's something like this. So up to this, R is 0. Slowly, I am increasing. There is a shear stress, finite shear stress. But at the center, the radius is 0. We are measuring from the center. So R is 0. So 0 into something, it is a finite value. 0 into something is 0. R is 0. So 0 into something, this is not 0. 0 into something, ye bhi 0 ga, plus C. So you get the value of C as 0. So therefore, R tau is equal to R square by 2 into minus del P by L. So tau is equal to, okay, 1 second please. 1 second please, don't be in a hurry. Second please. Yeah. Now, so tau is equal to, you divide with R. This R square is gone. R by 2 minus del P by L. What is he asking? Yield shear stress. Which one is yield shear stress? Look at yield. This is yield shear stress. Means up to below yield, there are no velocity gradients. Afterwards, there are velocity gradients. तो आपको यहां का कैलकुलेट करना है, because there are no gradients up to this. So yield is this value. When R is RC, put R is equal to RC, you get yield shear stress. What is RC? Anyone? What is RC? RC, somewhere he has given. Yes. RC is 0.001 meter. So therefore, if you want yield shear stress, put R is equal to RC, 0.001 by 2 into delta P by L. Already I know the value of delta P by L. How much is this? 10 into 10 power 3. So it is 10 into 10 power 3. Already delta P by L is done. So here 10 power 3. I think you are getting this 0.001 is 10 power minus 3, 10 power 3. This gets cancelled. 10 by 2, I think 5 Pascal. The answer is 5 Pascal. Where is that? Where is that? Where is that? Yes, this is the right answer. And this is a very good question, sir. This is a good question. Okay. Now let's move to the next question. Yeah, take this question. Please read the question. My dear students, please read the question. In the figure below, water exits from a nozzle. This is the nozzle. This is the nozzle. And water is exiting from a nozzle. Okay. Into atmosphere. And the pressure, atmospheric pressure is 101 kilopascal. If the exit velocity is 8 meter per second and the friction is neglected, the magnitude of the axial force on the flange, it is on. There is a flange. Actually, pipe and nozzle are connected with the help of flange. Let me explain, sirs. What is the force required to keep the nozzle attached to the pipe to the near? And the answer is given in Newton. Answer is required in Newton and dash. What is the question? Let us say there is a horizontal pipe of diameter 8 centimeter. Let me take this section as one. Let me take this section as one. And the fluid is leaving. There is a nozzle connected here. There is a nozzle connected here. And it is purely in the horizontal position. Great. And the exit velocity is given. It is coming out to atmosphere. Wonderful. It is coming out to atmosphere. No problem at all. You know very well, when the fluid flows, definitely the fluid will exert force on this attachment, that is flange. And you know, if it is not resisting, they will come out. For example, now there is a flange attached here. There is a flange attached. The fluid will flow, it will exert. If it is not supporting, if it is not resisting, it will come out. If it is not resisting, because of the fluid force, it will come out. But he is asking how much force is experienced by the flange to keep it in, to keep attached to this nozzle. Chalo, करेंगे sir, कोई बात नहीं. The first thing is, we have to apply 3 equations. One is continuity equation. One is, whenever you want to find out force, 3 equations are required. One is discharge, that is continuity equation. Second is Bernoulli's equation. And third is momentum equation. Let us do it neatly. So let this be 1 and let this be 2. I will write A1 V1 is equal to A2 V2. What is A1? Pi by 4 D1 square V1 is equal to pi by 4 D2 square V2. Pi by 4 is gone. D1 square V1 is equal to D2 square V2. What is the diameter? 8 square. 8 square into V1. I am calculating velocity here. Let this be V1 is equal to, how much is this diameter? 4. 4 square into V2. Already V2 is given as 8. Wait. I think 4 ones 4 hota hai. So I think V1 we are getting it as 2. Am I right? So therefore 16, 64, 4. 2 is correct. So here the velocity is, and one more thing, it is exiting to atmosphere. Okay, no problem at all. Let's do this, please. What I do is, please listen carefully. This is the flange. Okay, now 1 and 2, this is coming out to atmosphere. No problem at all. Wonderful. Dekho. Let me draw, let the pressure here, let me draw the free body diagram here. I'll take a small fluid element and draw the free body diagram. Look at. Let the pressure here be P1 and the area is A1. And this fluid, look at, all these I had clearly explained in my regular classes. So directly I'll draw the free body diagram. The fluid here, the left fluid will exert a force on this. And when this is exerting, and this element will exert on the right fluid and the right fluid will exert in the opposite direction. All these I had explained in my regular classes. Okay. Let the velocity here be V2. Let the velocity here be V1. I have taken a small element here both. And you know, actually we should take absolute pressures. But we are not taking absolute, gauge pressures are taken. Do you know the reason? I'll tell you. And this nozzle is surrounded by atmosphere. So atmosphere is exerting like this. So inside it is like this. So therefore, for example, atmospheric pressure is 100, let us say, and inside pressure is, let us say, absolute, let us say 300. Let us say absolute is 300. And you know, these two effects are nullified. So if I take this, so net force I am calculating 300 minus 100 is 2. That means it is gauge only, because whatever the pressure outside, it's something like this, my dear students. Try to understand. This was very important question asked by one of my students. So fluid to under flow ra, so therefore it has to be absolute pressure. Therefore it has to be absolute pressure, but you know it is also surrounded by atmospheric air. So inside atmosphere excess net will be what? Gauge only. So therefore now let us calculate. So if I apply my Bernoulli's equation between 1 and 2, P1 by W plus, and P2 will be 0, because already inside outside difference we are taking. Let me repeat, sirs. Let me repeat. Inside the fluid is exerting like this, outside there is atmospheric air. So inside actually I am taking absolute only. But whenever I want to calculate the net force, ये तो nullify हो रहा. There is atmospheric outside. Inside also there is some part of atmosphere. Both nullify and we are left with gauge only. So what is excess? What is excess? It is 300 minus 100, which is nothing but anything excess is gauge. So therefore I am taking gauge pressure. Okay. Now, therefore my P2 is already atmospheric. So as I am taking gauge pressures, ये तो 0 हो जाएगा. And please observe here clearly. And the pressure at 2 is atmospheric. So gauge pressure के लिए atmospheric will be 0. So therefore, now when the fluid is flowing like this, it will try to the flange will try to get detached. जब fluid exert कर रहा है तो यहाँ का flange detach होने की कोशिश करेगा. So therefore let F be the force required to keep the flange attached to the pipe and nozzle. So let this be the force. Now very simple, sirs. Very simple. Now net force. What is the net force? P1A1 minus F is the net force. P1A1 minus F, this is the net force. And you know momentum equation. Net force is equal to rate of change of momentum. What is rate of change of momentum? M dot into V2 minus V1. Because steady flow, mass flow, it will be same. So this is my momentum equation. What is that? Net force is equal to rate of change of momentum M dot into V2 minus V1. Now hold on. I want this F. I want this F. I can calculate F only when M dot P1, A1, V2, V1 are known. Already V1, V2 are known. So there is no problem. Let's try to calculate M dot. What is M dot? Either I can write rho 1 A1 V1 or I can write rho 2 A2 V2. Let's calculate M dot. Which fluid is flowing, sirs? Water. So therefore the density is 1000. Area. Which area? You are taking A1 V1. So what is A1? A1 diameter is 8 at 1. So therefore pi by 4 d1 square 0.08, 8 centimeter is 0.08 into V1 is 2 meter per second. देखो एक बार. Look at here V1 we have calculated it as 2. Already V2 is given as 8. So no problem at all. Either I can write rho 1 A1 V1 or rho 2 A2 V2. If I calculate this, dear students, if I calculate this M dot, let me check what is the value of M dot. I have calculated M dot. कहाँ गया रे? चलो फिर से calculate करेंगे. क्या करते हैं? 10.05. So I have no problem with the right hand side. Mass flow rate is known, V2 is known, V1 is known. So A1, what is A1? Pi by 4 into 0.08 ka square. A1 is also known. The only unknown is P1. If P1 is known, the force can be calculated. How to calculate P1? Apply Bernoulli equation between 1 and 2. P1 by W plus V1 square by 2G. It is horizontal, so no Z1, Z2. And losses are not given, so I will not take. So W can be written as, my dear students, W can be written as rho g, no problem at all. W can be written as rho g. So this is rho g, this is rho g. So, and P2 is atmospheric. Anyway, we are taking gauge pressures. So P2 is atmospheric 0. So P1, G can be cancelled. P1 by rho is equal to, you take V1 to that side, V2 square minus, see, my dear students, all these, how to take element and how to take force balance, all these I had explained very clearly in my regular fluid mechanics classes. So P1 is equal to rho by 2 into V2 square minus V1 square. So P1 is equal to rho is 1000 by 2. V2 is, I think we know V2. What is V2? V2 is 8. So therefore, 8 square, V1 is 2 square. You will get P1. कितना आ रहा है sir? 60, 30 into 10 per 3. This is 64 minus 4 is 30. Sorry, 64 minus 4 is 60. 60 by 2 is 30. 30 into 10 power 3 Pascal. So everything is known. Now just put it here, dear students. Everything is known. Let's substitute here. and calculate the value of the force required to force needed to hold this in position. एक second. P1 is 30 into 10 power 3. A1 pi by 4.088 centimeter minus F is equal to m dot 10.05 into V2 is 8, V1 is 2, I think. Is it correct? Yes, let me calculate. What? So 6 into 10.05. 6 into 10.05 is 60.3. 60.3. This value is coming out to be a value 150.7 minus F is equal to, this is 60.3. Okay, correct? 10.05 into 6. Yeah, 60.3. 150.7. So answer, the force required is 90.4 Newton. 90.4 Newton. See, the fluid is exerting like this, and the force resisted by this flange is in the opposite direction, which is, so it is offering the resistance. So 90.7. Thank you, my dear students. I'll come up with many more such questions. Thank you. God bless you.